Good morning to everybody. In this video, I am going to explain about the Fermi level in semiconductors. The probability of occupation of electrons and holes in valence band and conduction band is called Fermi level. That means the probability of occupation of energy levels of electrons in valence conduction band and holes in valence band is called Fermi level. Fermi level in intrinsic semiconductor. At absolute zero temperature, that means at 0 degrees centigrade, intrinsic semiconductor acts as an insulator. We know this property. However, as the temperature increases, free electrons and holes are also increases. So, if the recombination takes place, the same number of electrons and holes gets cancelled. So at the zero temperature, the number of electrons is exactly equal to the number of holes. Therefore, the Fermi level of the intrinsic semiconductor lies in the middle of the forbidden energy gap. It is exactly between valence band and conduction band, because here the number of electrons in intrinsic semiconductor, the number of electrons is exactly equal to the number of holes. Fermi level in the middle of the forbidden indicates equal concentration of free electrons and holes. This is the Fermi level diagram for the intrinsic semiconductor. Here the valence band and conduction band is separated by forbidden energy gap, and the Fermi level is located exactly between the conduction band and valence band, that is in the middle of the forbidden energy gap. Here the hole concentration is given by, generally the holes are present in the valence band. We know that. How we get the hole? The vacant place in the valence band is known as hole. So the hole concentration in the valence band is given by, holes are represented with P. So P equal to NV e power minus EF minus EV by KB into T, where NV is the effective concentration of the states of electrons, and EF is the Fermi level, and EV is the valence band, and KB is the Boltzmann's constant, and T is the temperature. The electron concentration in the conduction band is given by, the free electrons are present in the conduction band only. So the electron concentration in the conduction band is given by, here the electrons is represented with N. So N equal to NC, that is represented with conduction band. So NC is NC into e power minus EC minus EF by KB into T. These are the equations for the hole concentration in valence band and electron concentration in conduction band. The number of electrons in the conduction band depends on two conditions. One is effective density of states in the conduction band, and another one is distance of the Fermi level energy from the Fermi level, from the valence band to the conduction band. So there are two conditions affect the, two conditions influence the number of electrons in the conduction band. One is density, effective density of states in conduction band, and another one is distance of the Fermi level from the conduction band, because here electrons are towards the conduction band. The number of holes in the valence band is also depends on the effective density of states in the valence band, because the holes are present in the valence band, and the distance of Fermi level from the valence band. So for number of electrons in the conduction band depends on density of states in conduction band. For holes, density of states in valence band, and for conduction band, number of electrons in conduction band, it also depends on Fermi level, distance of the Fermi level from the conduction band for the electrons, and the distance of Fermi level from the valence band for the holes. For an intrinsic semiconductor, the electron carrier concentration is equal to the hole carrier concentration, because we know the number of electrons is exactly equal to the number of holes. So the carrier concentration of electrons is equal to the number of hole carrier concentration. That is written as P equal to N equal to Ni, where P equal to number of holes and N equal to number of electrons, and Ni is intrinsic carrier concentration. So the Fermi level for intrinsic semiconductor is given by EF equal to EC plus EV by 2, where EF is Fermi level and EC is the conduction band and EV is the valence band. Here why we are writing divided by 2? Because it is exactly located exactly between valence band and conduction band. That's why we are taking average of valence band and conduction band. Fermi level in n-type semiconductor. In an n-type semiconductor, we are adding penta. To get the n-type semiconductor material, we are adding pentavalent impurities to pure semiconductor. So here the pentavalent impurities has 5 valence electrons. So to form a covalent bond, it needs only 4 valence electrons. It has 1 excess electron. So it donates the valence electrons to the adjacent band. So it creates a free electron. It donates a free electron. So the addition of pentavalent impurities creates a large number of free electrons in the conduction band. So at room temperature, the number of electrons in the conduction band is greater than the number of holes in the valence band, because we are adding pentavalent impurities. So here only electron is donating, no holes are created. So at the conduction band, number of electrons is greater than number of holes. Hence, the probability of occupation of energy levels by the electrons in the conduction band is generally greater than the probability of occupation of energy levels by the holes in valence band. Because here in n-type semiconductor material, the majority charge carriers are electrons and the minority charge carriers are holes. So we can simply say that here number of electrons are more than holes. So that's why the Fermi level is towards the conduction band from the Fermi level. Therefore, the Fermi level in the n-type semiconductor lies close to the conduction band. That means nearly towards the conduction band. This is the Fermi level diagram for the n-type semiconductor material. Here the Fermi level is towards the conduction band. It is located towards the conduction band in the forbidden gap. The Fermi level for n-type semiconductor is given by EF equal to EC minus KB into T log NC by ND, where EF is the Fermi level and EC is the conduction band and KB is the Boltzmann's constant and T is the temperature and NC is the state of effective density of states and ND is the donor impurities, density of donor impurities. Fermi level in p-type semiconductor. In the p-type semiconductor, we are adding trivalent impurities to a pure semiconductor, then we will get p-type semiconductor. Here the trivalent impurities has only 3 valence electrons. So to create a covalent bond, it needs 1 more electron. So here it accepts 1 electron from the adjacent band. When it accepts electron, it creates a hole in the valence band. So the addition of trivalent impurities creates large number of holes in the valence band. At room temperature, the number of holes in the valence band is greater than number of holes in the conduction band. Hence, the probability of oxidation of energy levels that is by the holes in the valence band is generally greater than the probability of occupation of energy levels by the electrons in the conduction band. We can simply say that here in p-type semiconductor material, the majority charge carriers are holes, and why we are having majority charge carriers as holes? Because here we are using trivalent impurity. It creates one hole for one electron hole pair combination. So when adding impurities, trivalent impurities, it creates large number of holes. That's why it has large number of holes in the valence band. So it adds. Here we know the Fermi level. The energy levels occupied by the electrons or holes is called Fermi level. So here the holes are occupying more energy levels. That's why in p-type semiconductor the Fermi level is towards the valence band because the holes are present in the valence band. Therefore, the Fermi level in the p-type semiconductor is lies close to the valence band. This is the diagram for the Fermi level in p-type semiconductor materials. So the Fermi level for p-type semiconductor is given by EF equal to EV plus KB into T log NV by NA. We know what is EF, what is EV, and what is KB, and what is T. And here NV is the effective density of states in the valence band, and Na is the concentration of acceptor atoms. Nd is concentration of donor atoms. Na is the concentration of acceptor atoms. Fermi Dirac function. To know about the energies possessed by the electron in a metal, it is given by energy distribution function f of E. This is the diagram for the Fermi Dirac function. Here we are plotting a graph between E minus Ef on the x-axis. We are taking E minus Ef on x-axis and we are taking f of E on y-axis. So for different temperatures we are plotting a graph. So Fermi Dirac distribution expression. Mathematically, the probability of finding an electron in the energy state E at the temperature T is expressed as f of E equal to, the general equation for Fermi Dirac function is f of E equal to 1 by 1 plus E power E minus Ef by Kb into T. The Fermi level, here F is the Fermi Dirac function and E is the energy and Ef is the Fermi energy level and Kb is the Boltzmann's constant and T is the temperature. The Fermi level represents the energy state with 50% probability if no forbidden band exists. That is if E equal to Ef, at that condition the Fermi level represents energy state 50%. So in that case the Fermi level, that means 50% means if you substitute the values in the above equation, you will get Fe equal to 1 by 1 plus E power Ef minus E minus Ef by Kb into T equal to 1 by 1 plus E power 0. Then you will get E power value as 1, then 1 by 1 plus 1 equal to 1 by 2. Here 1 by 2 means 50% only. So to represent at no forbidden band, Ef is exactly equal to E is exactly equal to Ef, then Fermi Dirac function or Fermi Dirac equation is equal to 1 by 2. At 0 degrees Kelvin, there are two conditions exist. One is if E is greater than Ef, the exponential term, that is E power term, will becomes infinitive. Then Fermi Dirac equation f of E is equal to 0. At that condition, the energy is greater than Ef is indicated. If in the second condition, if E is less than E of F, the exponential term, that means e power term is becomes 0. At that time f of e, Fermi Dirac function f of e is equal to 1. So there are at 0 degrees Kelvin there are two conditions are exist. One is e is greater than ef. At that time exponential term becomes infinitive. So if the exponential term becomes infinitive, then Fermi Dirac equation equals to 0. At that time, taking the values or energies of greater than EF. Second condition is EF less than EF. That means we are considering values less than EF. Here the exponential term becomes 0. Then the Fermi Dirac equation equals to 1. At that time, we are considering energies less than EF. Thank you.